more about effects of intermolecular forces. We're going to talk about surface tension, viscosity, and capillary action. Of course, the most important thing about intermolecular forces is the fact that we even have liquids and solids. But there's some other interesting things. My husband is a fly fisherman, and that's not one of his flies, but he likes to do it whenever he has a chance. You can tie these flies, and you can throw them out on the water, and they'll float on the water. They'll just sit on top. And you've probably seen water bugs, water skaters, and they are walking on the top of the water. And it's like, how do they do that? And this is a fun trick. You can float a paperclip on water. Now, normally, things that float need to be less dense than what they're floating in, right? This paperclip is probably made of stainless steel, some metal. Metal doesn't float in water. So how's this paperclip floating? And it's not doing the boat thing. A boat can float because it displaces water. This isn't displacing water. But you see how the water is bending? Almost like there's a skin on top of the water. Like you put a piece of saran wrap on top of the water and you put the paperclip on top of that. There actually is kind of a skin on top of the water. And it has to do with, it's called surface tension. It has to do with intermolecular forces. So surface tension is the tendency of liquids to minimize their surface area. They're trying to be smaller surface area. It can be quantified. It's the energy required to increase the surface area by a unit amount. You specify what unit. So if we quantify the surface tension of water, 72.8 millijoules per square meter. So to increase the surface area of water by a square meter would require 72.8 millijoules. But this is, surface tension is what allows trout flies, paperclips, water skaters to float on the water even though they're more dense than water. Has to do with intermolecular forces. If we look at the surface molecules, so here's an illustration of water. We're just going to make them blue balls because we think of water as being blue. And actually water does have a color. It is a very, very pale blue. So here are blue circles instead of the usual red and white Mickey Mouse heads. So up here on the surface, the water molecules at the top interact with other water molecules on the top and with the ones on the inside, but there's nobody above to interact with. Water molecules on the interior interact in multiple directions, and they're going to interact with more molecules than the ones on the surface. So if we were to increase the surface area, we would have to move some of these interior molecules to the surface. Because there's a certain number of molecules on the surface, and if we're going to make the surface area larger, some of these guys are going to have to come up and be on the outside. To do that would require energy, because this guy is more stable here. He's got all these nice attractions. He's really happy, and you're asking him to move to the edge of the forest, you're asking him to be a pioneer and leave all of his family behind and go live on the edge of nothing. And that would require a lot of energy. And because that requires energy, the liquid does not want to do that. And so it's going to try to minimize its surface area. The surface tension will decrease as the intermolecular forces decrease. Let's just go back to this picture. If it's the strength of attractions for the interior molecules that is causing them to not want to go up and have fewer interactions, if these interactions are weak, then going to the surface isn't as big of a deal, and the surface tension is less. If these forces of attraction are stronger, then losing 2 forces here to only have 4 is going to be a big deal. And it's not going to want to do that. The surface tension will be greater. So surface tension is directly related to intermolecular force strength. This picture is a an astronaut, and this is a drop of water floating in space. We don't normally see drops of water that are that large, right? Because there's a force of gravity pulling them down. But in space where there's no gravity, you can push water together and it'll just form a big sphere. And, obviously astronauts have a little bit of a playful side. And, you're up there in no gravity. You might as well have some fun, right? You can't watch Netflix. So you've got to do something. So they're playing with water. But why do water droplets make spheres? Why don't they make cubes? Well, the sphere is the shape with the smallest surface area. So to get the smallest surface area, it's going to form a sphere. When you get really tiny water droplets, they're nearly perfect spheres. Here on Earth, when you get larger ones, they get distorted by gravity. So, we typically would draw a drop of water as being more shaped like this, right, as it's falling off the faucet. But that's because it's being distorted by gravity. When you make a fine mist and spray droplets of water into the air, if you were able to look at them, they'd be perfect little spheres. Viscosity is another one. And I don't watch much TV, but those oil commercials. What are they always talking about? Viscosity breakdown. You don't want viscosity breakdown. Well, you don't. But every time I see the word viscosity, I think of motor oil. What is viscosity? It's the resistance of a liquid to flow. This can also be quantified and measured. It's measured in a unit called the poise, a P, and it's a gram per centimeter second. So we're just kind of telling you that. If we look at these different hydrocarbons and look at the measure of their viscosity, we see that the viscosity increases as the molar mass increases. These are similar compounds. They're hydrocarbons, just hydrogen and carbon. They're all nonpolar, and they're all long chains. And so as this gets larger and larger, what's happening to the dispersion forces? They're getting larger, right? Because it's more easily polarized because it's larger, but also these chains are longer and they've got more surface area to stick together. And so we see that the viscosity, the resistance to flow, increases with the increasing molar mass. Another thing that's kind of interesting with these hydrocarbons, because of the rotation around single bonds, not only can they be in a straight line, but they can also twist around on themselves, and they can actually get tangled up in each other. And so that increases the viscosity even more. So strong molecular forces, higher viscosity. It also depends on temperature. So honey or pancake syrup or molasses or corn syrup, these are viscous liquids that you might have in your kitchen. So let's think about honey. When you pour honey out, it pours slowly, right? We say it's thick. It doesn't pour in a thin stream like water does. It pours in this big glob, and it's slow. It has resistance to flow. It has high viscosity. What happens when you heat honey up? It gets thin and runny, right? Same thing with pancake syrup. You heat it up, and the viscosity decreases. So viscosity depends on temperature. Because at higher temperatures, you've got more thermal energy, and that's going to partially overcome those intermolecular forces. So it has to do with the relative strengths of the thermal energy and the intermolecular forces. So this is why they're so on viscosity with your engine and your oil. So your engine gets hot, right? Especially here in the valley in the summer, the engine gets really hot, right? When your engine gets hot, your motor oil gets less viscous. The oil needs to be coating the inside of your engine and lubricating the parts. If it's too inviscid, if it's too liquidy, if it's lost its viscosity, it's not going to coat everything, and then you get metal on metal and really bad things happen. Like your engine freezes up. They say it freezes up, but it's actually because of really high heat. They kind of fuse together. Yeah, it bonds together. You got metal on metal, and it got so hot that it just like fused, it welded itself together. Yeah, and that's going to be really, really expensive. But then at cold temperatures, it becomes more viscous. And so you take honey and you stick it in the freezer, and it's going to get thicker and thicker and thicker. Well, if your motor oil is too thick, it can't get around and coat your engine either. And so blending motor oil is actually a science, and they've done a lot of improvements. So modern motor oil, they have polymers in there that will coil up at high temperatures to increase the viscosity, but then at low temperatures they unwind so that they're not increasing the viscosity. And this allows your oil to maintain a more constant viscosity even through very low temperatures and very high temperatures. When I was growing up in Minnesota, you had to change your motor oil in the fall. Because, you get up in the morning and it's minus 30 degrees. Okay, the oil that worked really well when it was 80 degrees in the summer is not going to work right now. It's like Jell-O in your engine, right? So that's not good. So that's kind of cool. Capillary action, that's the other one I couldn't think of. Capillary action has to do with intermolecular forces too. Capillary action, the ability of a liquid to flow against gravity up a narrow tube. So these are capillary tubes. They're very small glass tubes. When you stick them in liquid, the liquid just comes up all by itself. This doesn't work on a drinking straw. It's too large. It needs to be a narrow tube. And these two tubes have the same inside diameter. This one has a larger inside diameter. The larger the diameter, the less the height of the liquid is. And capillary action comes from two different forces. There's cohesive and adhesive forces. So cohesive forces are the attractions between the molecules in the liquid. So a cohesive group, everything's like sticking together really well. So those are the intermolecular forces. Adhesive forces are the attractions between the liquid and the surface of the tube. So we've got cohesive forces, which are trying to keep all the liquid together, and adhesive forces, which are causing the liquid to crawl up the tube. So if adhesive forces are stronger, the liquid will rise. If they are not stronger, the liquid will not rise. This also has to do with our friend, the meniscus. So here's water. Water has a concave meniscus. So it's going down. It looks a little bit like somebody dropped a contact lens in here. And it's got a curve to it. And we've learned that we measure to the bottom of the meniscus. Well, mercury has a meniscus that goes the other direction. The mercury meniscus is convex. It curves up. And this has to do with the relative strengths of cohesive and adhesive forces. Why are the edges of the water surface bending up? It's because of adhesion. These water molecules have adhesive attractions to the glass, and so they're going to try to crawl up. They can't crawl up very far because this tube is way too wide. So you're not really going to get capillary action. But there's just like this beginning. We want to go up. We want to go up. In the mercury, the attractions between the mercury atoms are greater than the attraction of mercury for the glass. And so we see this opposite. It's trying to make a sphere at the top here. It's trying to decrease its surface area. And it's not wanting to associate with the glass. Now, you can change this if you use different substances for your tube. This is what happens with glass. There are certain plastics where you could get water to do this as well. If it was a hydrophobic plastic and repelled the water, then the water would also do the convex meniscus. There, we'll stop there for today.